Question 3. Table shows boiling points of ammonia, fluorine and bromine. Explain the different boiling points of these three chemicals. Include the names of any relevant forces and particles. So this is a very good example of a question where you're being expected to compare different types of intermolecular force. You've got to be able to work out and spot what intermolecular force you've got present in the molecules that are here, compare and contrast them, and talk about the particles involved in the forces as well. There's a lot of information going on in this question, and historically these are the sorts of things, when it comes to structure and bonding, that first year students particularly find difficult to do. So let's break this question down first of all, and let's just ignore any of the information we've got here and focus on the three chemicals that are involved. Ammonia. So you look at the molecule first of all, look at its chemical formula, the atoms and elements involved in the formula. We've got to decide whether or not we've got permanent dipoles, hydrogen bonding, or London forces, and the same for fluorine and bromine as well. Okay, well, think about what we've got. A hydrogen bond is the attraction from a lone pair on a highly electronegative element from one molecule to the hydrogen of another. Now, nitrogen is definitely highly electronegative, okay? It's the third most electronegative element on the periodic table, so it's definitely highly electronegative. We've definitely got a lone pair as well on that nitrogen. So in here, I'm going to have hydrogen bonds between the molecules of ammonia. Now, we already know that hydrogen bonds tend to drastically increase boiling and melting points because they are the strongest intermolecular force in comparison to the other two, the permanent dipole interactions and your London forces. Now, fluorine and bromine, molecules on their own, there's no difference in electronegativity between the two fluorine atoms, likewise with the two bromines. So these molecules are not polar. So for both of these, we will have London forces. So let's look at the boiling point. So without looking at that, what would you expect? Well, we know the hydrogen bonds are stronger than London forces. So you might expect then that the ammonia would have a higher melting and boiling point than both the fluorine and bromine. Now, if we look, we can see that ammonia is minus 33, definitely higher than fluorine, but bromine is 59. So bromine has got the highest boiling point. And it's that point students go, well, that doesn't make any sense. I've been told that hydrogen bonds are the strongest ones, therefore that would have the highest melting and boiling point. This is where you've got to draw in on all the information and understanding about how London forces in particular arise. Now, if you remember back to when this was taught to you, you will have learned that London forces arise purely due to random motion of electrons. And the more electrons that the molecule or the atom has got, then the more and therefore the stronger London forces can form. Now, if we do a direct comparison then on the electrons in ammonia and fluorine, okay, and then bromine, and that will then hopefully give us an explanation of what's going on here. So an ammonia molecule has got a nitrogen atom and 3 hydrogens. Okay, now a nitrogen atom has got 7 electrons. So we bring the periodic table in. Okay, we know the atomic number of nitrogen is 7. And then there's 3 hydrogens, each providing 1 electron each. So 7, 8, 9, 10. There's only 10 electrons in the ammonia molecule. Let's write that on this side. There's 10 electrons there. Fluorine, 2 F atoms even in the molecule, gives us 18 electrons. So there are slightly more electrons in the fluorine than there are in the ammonia. Bromine, down here, has got 35 electrons per atom. That's 70 electrons in the molecule. Drastically more than the 10 that's in ammonia, and therefore the 18 in fluorine. Now, because of that then, because we've got such a bigger number, greater number of electrons here, that has increased the boiling point above that of ammonia, despite the fact that ammonia has got a hydrogen bond. So ammonia and fluorine being very similar to each other, you would expect the boiling points to be very, very similar, roughly the same. But we've got a massive increase from fluorine to ammonia, with only an 8 electron difference. So that hydrogen bond present in ammonia must be significantly increasing the boiling point. Then with bromine, because we've got a significantly higher amount of electrons here, we've got many, many more London forces forming, which then must be stronger in total than the 1 hydrogen bond you can get between the 2 ammonia molecules. So the strength of the intermolecular forces is relative against for one of those forces. One hydrogen bond is stronger than one permanent dipole-dipole interaction, which is stronger than one London force. But the combined effect of many, many London forces can make that stronger than one hydrogen bond. So you've got to factor in the number of electrons present as well when you're cross-comparing different types of intermolecular force. So that is all the information you need to have to answer this question. So what I'm going to try and now do is summarize what I've just told you into a few of the key bullet points here. So what do we say? Look at the question again, explain the different boiling points, include the names of relevant forces and particles. So let's start with the forces. Let's start with ammonia. Let's break it down per type of chemical. Ammonia. The force involved here is hydrogen bonds. And they're forming between molecules, because that's the particle that is involved. We've got ammonia molecules, fluorine molecules, and bromine molecules. Hydrogen bond is occurring between the ammonia molecules. Okay, fluorine and bromine. So both of these have London forces between the molecules. So again, I'm stating the particles. Okay, and that's the bit that's commonly missed out. When you see that, it's asking you to say where the attractions, where the intermolecular forces are forming in between. Okay, so that's stating that the types of bond and type of intermolecular force and the particles in which they're forming in between. So that's explained the difference. So what we can say is ammonia has a higher boiling point, I'm going to put BP for short, than fluorine, because the hydrogen bond is stronger than the London forces present, needing more energy to overcome. Okay, so explaining the difference between the ammonia and the fluorine there. Okay, we've also then got to explain the difference between the ammonia and the bromine and the fluorine. So you've got all those comparisons going on. You've got to make reference to them all, which is why this question is so difficult to get all the marks for. If you try and take shortcuts and not talk about everything going on. Okay, so you can see I'm trying to highlight some bullet points or some key areas to focus on. So we've got type of forces, type of particles, now explaining the differences. So we explain the difference between ammonia and fluorine. Okay, now we can say that ammonia has a lower boiling point than bromine because there are many more electrons in bromine, making the London forces stronger than the hydrogen bond. And needing more energy to overcome. Okay, so we've explained the difference between ammonia and bromine. So now between fluorine and bromine themselves. Okay, so we can also say that bromine has a higher boiling point than fluorine because it has more electrons. Which means there are stronger London forces needing more energy to overcome. Okay, so the answer I've written there, there is quite a lot of repetition in there. I've said need more energy to overcome 3 times. You probably wouldn't need to do that, but I'm trying to make it nice and clear for you. all the comparisons that are going on to answer this question in full. Okay, so you can't try not to take shortcuts. You can bullet point your answers by all means, but still make sure you're explaining all the possible comparisons that are present there. So at this point, I'd like to bring the mark scheme in just so you can see exactly the marking points the exams will be looking for here. Okay, and I can relate that back to the question. All right, so if I bring the mark scheme in, we can see here, mark number 1, it says NH3 forces mark. So 1 mark for stating simply that ammonia has hydrogen bonding, which we've said here. Mark number 2 is for the fluorine and bromine forces mark. So statement that fluorine and bromine have van der Waals. It's an old mark scheme. Van der Waals, the term van der Waals has now been replaced by London forces. So fluorine and bromine both have London forces, which we've said here. So there's your first 2 marks. Mark number 3, we bring the next page of the mark scheme in. Types of particle mark. Now look, all they're doing here is breaking down the instructions in the question. Remember, the question stated, name the forces and the particles. So before you even get to any explanations, as long as you've named everything correctly, you get the marks. Okay, so here, mark number 3, forces or attractions are between molecules or intermolecular. Okay, for ammonia, and forces are between molecules for the fluorine or the bromine. So again, what we've said here, because I've said between the molecules on both of them, I have satisfied that mark. Okay, mark number 4, the bromine-fluorine comparison. So the London forces in bromine are greater than in fluorine because bromine has more electrons than fluorine. So that's the last statement I've written down at the bottom there. It has more electrons. So bromine has a higher boiling point than fluorine because it has more electrons. Okay, and it says the van der Waals forces are greater. So we've mentioned the fact they are stronger there as well. Okay, and mark number 5 is, it says a bromine, ammonia and fluorine comparison. So the van der Waals forces or London forces in bromine are greater than the hydrogen bonding in ammonia, and the hydrogen bonding in ammonia is stronger than the van der Waals. So that's why I've broken it down into the 3 areas and done the 3 comparisons separately. That way you're ensuring you're covering all the possible boundaries, all the possible comparisons that are going on. And that's where the problems lie. If you try and take a shortcut with this, you might miss a key explanation, you might miss one of the comparisons, and therefore you'll drop marks. All right. So tips for any question involving boiling points. Okay, boiling points and melting points are a physical property directly related to the strength of either the bonding or the intermolecular forces. So you've got to decide: are you looking to break ionic or covalent bonds or metallic bonds, or are you overcoming intermolecular forces, or are you even comparing one against the other? All right. So look out for that. Boiling points are always going to be talking about breaking bonds, overcoming forces, and all your explanations to do with melting and boiling points should all make some reference to the energy needed to overcome. How much energy does it take to break a bond? How much energy does it take to overcome an intermolecular force? Comparing them against each other. But that is the key thing that you need to bring your answer, you need to direct your answer towards, a statement that can allow you to say more or less energy is needed to overcome these forces or bonds.